In this video, we will discuss the proof of the simple comparison test. Okay, so what does the simple comparison test say? Well, the setup is that we have two sequences of real numbers and some constant k such that eventually both sequences are non-negative. So this condition here is saying that once we get past the point capital N in the sequence, AN is non-negative, and therefore by implication BN is also non-negative. And we have this constant K that bounds the terms in the sequence AN by the corresponding values in the sequence BN multiplied by K. Okay, so in this scenario, if we have this comparison between the terms of the sequences AN and BN, then the convergence of the bounding series BN implies the convergence of the series AN. Now, you could restate this. Given that we know the series BN converges implies that the series AN converges, you can state the contrapositive of this theorem. If AN diverges, then necessarily BN must also diverge, because if it converged, we'd have a contradiction. So the contrapositive of this theorem tells us that if we have this same set of assumptions, then if AN, the series AN, diverges, then the series BN also diverges. Okay, so the critical features to really make sure you've understood in the way this has been stated is that we're assuming that beyond some point the sequences are non-negative sequences, and that we have control of one sequence by a multiple of the other sequence. Alright, so how does the proof go? Well, the first thing to note is that the reason why the statement of the theorem only requires information about the sequences beyond some point capital N is because, as we saw in the first series of videos for the first workshop, if we want to know whether or not a sequence converges, it's enough to look at the tail. The convergence of a series depends on its tail. So this is just something that we saw in the first sequence of videos. And similarly, we know that the tail of AN converging happens if and only if the whole series AN converges. So if we want to prove this theorem, namely that the convergence of BN implies the convergence of AN, it's sufficient for us to just look at the tails and prove that if the tail of the BN converges, then the tail of the AN converges. Now, how does the logic flow through here? Well, essentially, we want to show that if this converges, this converges. We know that this converging implies this converging, and if we could show that that converging implied that the tail of the series AN converges, then we would also know that this implies this, and hence putting it all together, this implies this, which implies this, which implies this. Namely, this implies this. Assuming, that is, that we have shown this implication to be true. So that reduces the proof to just figuring out whether or not this implication holds. And that's why we only really need to know something about the series, so the terms in the series beyond the point capital N. Okay, so the meat of the proof goes as follows. We're trying to show that on this assumption that the tail of the BN series BN converges, we're trying to show that that implies that the sum of the AN must converge. Right, so we start by assuming that the sum from capital N to infinity of Bn converges. By definition, that means that the sequence of partial sums converges, and a sequence that converges must be bounded. So we know that if we denote the sequence of partial sums of the series Bn by T subscript m, it converges, and so it must be bounded. So the sequence Tm is bounded. If something's bounded, that means that there is some constant capital L that is an upper bound for the sequence. So we can find some L in some real number L such that Tm is less than or equal to L for all possible m. And the possible m in this case are the ones greater than or equal to capital N. So for each m, we know that this partial sum is just some finite sum of numbers, and the conditions on the theorem tell us that for all n greater than or equal to capital N, these terms are less than or equal to k multiples of these terms. So this partial sum must be less than or equal to this whole partial sum. That's just adding up a finite number of inequalities. Okay, now a finite sum we can just pull a constant out without any concern. So we know that this partial sum is less than or equal to k multiples of this partial sum, but this partial sum is just the thing that we denoted by Tm up here, so we know that this partial sum must be less than or equal to the constant k multiplied by the constant L. So we have KL as an upper bound for this sequence of partial sums. Now, we've assumed that the AN are eventually positive, in particular beyond the point capital N, the terms AN are greater than or equal to 0. So this sequence of partial sums involves adding a non-negative value on each time. So this sequence must be non-decreasing, and hence it's a convergent sequence by the monotone convergence theorem. It's a non-decreasing sequence that's bounded above, so it must converge. And that is, we've shown that this infinite series converges. So we've concluded that the convergence of the series Bn implies the convergence of the series An, which was precisely what the statement of the theorem tells us. Now you should go on and watch video 2C, which gives the proof of the limit comparison test.